Hey, good morning. Is everyone having a good conference so far? All right, good. Well, I'm honored to speak with you guys today. Just to introduce myself, my name is Jeremy Carroll, and I'm a site reliability engineer at Pinterest. I work in the cloud engineering team, which we're responsible for a lot of the foundation platform that runs Pinterest as a whole. And today, I'd like to talk to you a little bit about service discovery and do more of a technical, in-depth talk about how Pinterest runs service discovery on the cloud. As a show of hands, it's kind of an informal thing. How many people actually run a service discovery type system in production? Good. So more hands than I actually thought, maybe like 25–30% or whatnot. So what I like to actually describe is basically a little bit about what service discovery is, how we actually choose to do it, and basically the idea is that more people do microservices or other things in production. I think that service discovery will become a core piece of infrastructure if you don't run it already. To give you a little bit of idea about Pinterest, what Pinterest is in a nutshell, it's a visual bookmarking tool that helps you discover and save creative ideas. An example is that I have a screenshot of my home feed, which is the main thing you see when you go into the Pinterest application. The current things that I follow is things like DIY, Geeks Tech, so I can actually like see Sonic the Hedgehog. That was pretty cool. And other things that I can actually discover and save for later. So at Pinterest, we have the pin it button where you can go around the web, and as you see content or ideas that you want to save for later, you can pin them to a collection of ideas called boards, and then save those boards to actually go back later and hopefully do those things in real life. So with that, just a little bit of the agenda. So I'd like to talk to you a little bit about what service discovery is, in a nutshell, kind of the main points and why it's an important part of infrastructure. Second, I'd like to talk about how we chose Zookeeper at Pinterest to power most of our discovery engine for the systems we run. We use Zookeeper for a lot of other systems at Pinterest, such as dynamic configuration, but we'll be talking a lot about that today, just mainly about service discovery. And then finally, talking a little bit about how that influences monitoring stack, and where I kind of see the challenges in the future. To give you a little bit of idea about Pinterest, we don't actually have any data centers at all. We run 100% on Amazon Web Services, so we don't actually have a fixed size asset or fleet for anything. So as we employ techniques in the cloud like auto-scaling, where we bring more instances into production to serve our services, it's very dynamic in general. So having a service discovery system is very helpful, which I'll describe in a little bit. So the service discovery is a pretty easy concept. In general, you want to provide either a strongly consistent or a view of a central service registry. So as more people start adopting microservices or service-oriented architectures, they need a place for other people's code to know how to connect to those services. So in general, there's three main methods which we kind of go through. And it's pretty simple as a nutshell, but it's kind of a powerful concept actually when you actually apply it. So for example, you have to provide a method for your application code to register itself to the service discovery system. And in general, at Pinterest, what we do is that every application itself will open up a connection to Zookeeper and register its availability once it's healthy to serve traffic. And then in general, we'll recommend that individuals do not put DNS information inside that registration, because it's a little bit orthogonal to have another discovery service actually register discovery information to the discovery system. So it's kind of, so we don't do that. In general, also, when we register service discovery, we put your IP and port combo so that other people know how to connect to you, because ultimately that's what people want to know. And then we also put what environment you're actually going to connect to. So for example, you'll say, I'm going to register myself as a, for example, data service serving production, or I'm going to be a data service serving prod or QA, or vice versa. The second method is looking up the service. So for example, from a consumer code, you are a client and you want to connect to a service, you need to connect to the registry and say, give me information on how to connect to that service. So what we'll do from a code perspective, you'll say, I want to connect, in the previous example, to data services prod. And then basically you'll be presented with a list of information, which allows you to connect to that service. In our case, usually a list of IP addresses and port combos. And then a really important critical aspect of this is notification when things change. So since we're in a dynamic environment, Amazon really doesn't give us a lot of warning when things fail or crash, or if unexpected load increases come, we're going to have to scale the size of the fleet. So everybody has to know about that. You have to say, hey, here's new entries inside of your service, here's how you connect to them, so you please take advantage of them. And in general, the application has to handle that reconfiguration logic gracefully. An example is that if your application is using thread pools or some other type of resource to save downstream services, it has to reconfigure itself. So service discovery is just one aspect of the system, but there's a lot of requirements in the code to actually take advantage of that and do that. So I want to kind of show a little bit about how application routing kind of works at Pinterest in kind of a simple way. But in general, what we've done is over the time, we used to run a way long time back, something like one application per host, which made sense at the time. And it was pretty easy to get an idea without service discovery, what you're doing. You set something like Web 001 or Web 100, and then you just register yourself with a load balancer or whatnot. That usually works fine. But then as things start failing or you guys are scaling it out, you need something like this. So we actually started running more than one copy of our application per instance. And for example, a lot of our web server fleet runs gEvent, which is a Python-based scheduling framework, so that it's single-threaded, but basically allows cooperative multi-scheduling inside your code. So with that, we run multiple copies of that per web server. So we have 16 CPUs, maybe we'll run 16 copies of that, for example. And then we use resource containment techniques to actually keep them inside their system so they don't have cross-deflect or cross-bleed on that. And then ultimately, we use client-side load balancers in our service-oriented architecture to connect all these things. So for example, if it wants to actually talk to a service, it's responsible for load balancing all those connections. It will actually do round robin or random, usually we choose random, to actually connect all the different hosts. And then how the actual registration works in our environment has worked relatively well, is we have the applications themselves registered with Zookeeper. What that means is that they'll actually make a connection out to the main quorum, and they'll register themselves as long as they're healthy. As soon as they're unhealthy, they'll deregister themselves, and then everyone else will be notified of that change. But unlike most of the people, we run a lot of open source code, and we're not going to modify every open source package out there to directly register with Zookeeper. So that month we actually wrote a little sidecar daemon or application that runs on each one of the hosts that can register on your behalf if you're unable to. An example of that is that sometimes we have varnished load balancers, and we have some code maybe in a different language that we don't support officially. And then what it'll do is it'll use that third-party code to monitor its health on its behalf, and then register with Zookeeper. And then the consumer code that will read from Zookeeper and then update varnished rules relative to HA proxy rules or vice versa. So that's kind of a nutshell of actually how at least the service map components work and how things actually discover themselves. So I want to talk a little bit about the system we actually use to power all this is Zookeeper. And kind of go over the reasons why we actually chose Zookeeper and some of the battle stories. I think everyone's got a Zookeeper story that uses that out in production. We have a share of ours. And then in general, just how we scale that technology to actually meet our demands as we do more and more services and put them in production. So the main question we have to ask is why did we choose Zookeeper? So many years ago, I had a choice in what to do for service discovery systems. And we found that we had Zookeeper in production for a lot of other use cases. We're running HBase, we're running Kafka, and other types of systems that require Zookeeper for locking, distributed locking, or consensus. And since we have to run those systems and we have to gain expertise on them, we might as well say, okay, well, just choose this one. Also at the time, there wasn't a lot of choices. For example, etcd is gaining popularity, and other type of systems that weren't existing at that time. One other thing that was actually nice as well is that we weren't the largest customer of this. Other companies like Facebook and Twitter had pushed Zookeeper to scalability limits a lot further than we actually had. And it was nice to know that we weren't going to be the largest customer that's kind of pushing the boundaries of the system. And it was widely tested and proven. So I know that Carroll, I think Serge doing some talks here today, but he did some Jefferson tests on it. So for its consistency story, it's actually pretty good. And then the client implementation in different languages was good. So for example, we have 3 primary languages at Pinterest, being Java, Python, and Go. And so usually we use Curator for the Java clients, and then for Python we use Kazoo, which is a native implementation of the Zookeeper protocol in Python. And then we use the Go client library. The name escapes me at the top of my head. But before I actually go into talking about how we actually architect and scale Zookeeper to serve the system, I just want to give you an idea of some of the roles of the system. In general, the main quorum is actually comprised of an odd number of hosts, usually 3, 5, or 7. The reason why is because to actually vote and actually have the quorum and ensemble work, there has to be a quorum. So you don't necessarily want to have an even number of hosts in there. And also additionally, the more nodes you add to the system, the slower it can actually get. So it's a little bit backwards to think that if you want more scale, you add more nodes. Actually, more things in the voting algorithm itself actually makes the system slower. So with that, we actually usually choose for availability 5 or 7 nodes inside of production. And also in general, the main quorum's main scalability factor is write throughput. So write throughput. So there's a good story, and I'll talk about a little bit about that to actually scale some of the reads from the system, but the writes are actually limited quite severely. So you have to capacity plan to make sure that that's actually good. One thing that when we're actually operating Zookeeper at Pinterest that we didn't see a lot of documentation on is the correct use of observers. So one thing that we kind of brought to production. But observers are effectively a non-voting member of the main quorum. And that does really help you a lot to figure out actually what it does. So basically, they're a key part of scaling the system. So in certain versions of Zookeeper, the observer is more effective at scaling the read load than others. But effectively, it can take some of the read load off of the main quorum to basically make it where the main quorum only does writes and the observers do the reads. And in general, I'm going to give you some advice a little bit later about what version of Zookeeper to run, because there's quite a bit of difference between the version of 3.4 branch and the 3.5 branch, which I'll detail in a little bit. But this is the general architecture of how Zookeeper works for the service discovery system at Pinterest. The main idea is that if you're not familiar with Amazon Web Services, they have a concept called availability zones. Availability zones is basically data centers that are very closely located to each other, so they have kind of land-like access properties all on the East Coast. At this time, Pinterest was located in US East, so that all of our properties are actually in that availability zone. In that region. And then for making sure that if we lose one data center, we can stay online to serve, we actually split the main quorum up so that if we lose one data center, we're still okay, we're still online. And then we run observers in each availability zone to proxy the writes and reads to the main quorum. In general, the applications themselves never talk to the main quorum. The observers will actually do reduce the connection load on the main system. And so whenever you want to talk to it to either register a service, look up a service, or vice versa, you'll connect to the observer and it'll proxy that on your behalf. And in general, if you run the version 3.5 branch, which I recommend that you do test, but trust but verify but test it. But the 3.5 branch, technically, if you go to Zookeeper right now, go to the Apache website, is 3.5-0-alpha. So it's technically an alpha, but it's been around for a long period of time, and a lot of companies actually run this at scale. But the main reasons why we run the 3.5 branch is there's a lot of improvements in the scalability of the system. We actually did a couple of blog posts at blog.pinterest.com about how we took famous outages of our Zookeeper service discovery system. One of them actually results in a multi-hour downtime that we did some mitigations towards. And after that event, we did a lot of investigation into how we actually would architect the system to serve. An example is that the current main form right now, I just checked a little bit ago, so there's about 150,000 watches right now. So what that means is that every time you register a service and somebody wants to know if there's a change in that service, they'll register a watch and then notify when that changes. So there's a lot of load in there that's potential about dynamically reconfiguring yourself. So talking about a little bit about observers. So observers actually, in the 3.5 branch, take a lot of load off the main quorum. And then going into a little bit of detail about one of our outages, we actually had a bug in one of our client implementations about the reading of information from Zookeeper. So in Zookeeper in the 3.4 branch we're running, every time somebody wants to read some information from the observer, they have to connect to it. And connecting creates a session. And Zookeeper the 3.4 branch, a connection in a session creates a write on the main quorum. And since I said that the scalability throughput and the bottleneck is mainly on writes, we had a bug where as soon as the main quorum got a little bit of destabilized, the clients would actually not load shed, not fail fast, not time out, and then connect faster. So basically we added to a metastable outage, which means that the amount of load coming into the system actually stabilizes the availability event. So we actually had all the nodes, like 10,000s of machines or vice versa, all connected back to the main quorum just to get the data. And all doing it kind of in harmony, just smashing the system to pieces. And then what we kind of learned is that in the 3.5 branch, there's something called local sessions, which was kind of the key for us to stabilize and scaling the system. What local sessions allows the observers to actually take all the connection load off the main quorum. So that means that every time a connection comes, it actually is serviced fully by the observers. The observers also have a full copy of the entire Zookeeper database, so they can serve all the reads locally without even consulting the main quorum at all. And the only time they actually talk to the main quorum is if there's an event which requires them to be promoted to what they call a global session, and then that will then talk to the main quorum. So for example, when you register yourself as available to serve for a service, you'll put yourself in an ephemeral node inside the system, which means I'm only alive as this node is only registered for the service as long as my connection is alive, and that's a write on the main quorum. But then the rest of that information can actually be serviced all by the observers. In addition to that also, we chose just to get a little bit of information about the size and the shape of this fleet. We use the C3 2X large instances for Amazon for SSDs, and then kind of put some of the configuration and tuning options that you can can't read that, maybe a little later on the slide, what kind of use. And the main thing is that we enable local sessions. We set the global outstanding limit, which is basically how many connections you can have in a queue to handle thundering herd events. And we set that relatively higher because usually they're temporary and that can absorb the blast at the cost of memory. And then the JVM options, we usually set the new size to be a little bit higher so it can handle all that connection load that maybe comes on in. And it kind of just showed a little bit of graphics. So this from our internal observability tools, when we made the switch over, we actually looked at the effect that actually local sessions in the 3.5 branch had on the main quorum, and kind of looking at just the drastic reduction in the amount of information kind of going to the main quorum. In addition to that, and the observers have something called a read-only mode, which most people do not know about. But the read-only mode basically allows the observers to serve stale data if they cannot connect to the main quorum. So for example, when we had that outage in the main quorum, the observers stopped serving all traffic, so basically they're dead in the water. With that option, you can basically say that if the main quorum's offline, I'll serve stale data. I'll actually factor availability over consistency. And then the clients themselves can register their intent if they want to actually read stale data. So when a client connects, they'll set something called a read-only flag, and then basically if that's the case, if they lose connection to the main quorum, they'll still stay connected to the observer, and all the other ones that want synchronous communication will be disconnected. So it basically allows you to kind of choose your availability consistency story when it comes to that system. Sorry, I'm getting over a cold. But basically in production, so what we kind of learned is that the service discovery is a critical part of infrastructure, so availability over consistency is key. So by reconfiguring the system to use read-only mode in observers and scale that, we can actually gain close to almost near 100% uptime. In addition to that, we talked a little bit about cascading outages. So basically our client connection code has to be robust. So even if we're actually using other systems, if you don't necessarily use Zookeeper for your environment, there's some patterns that we kind of learn in general working with this type of system. In general, the thundering herd. So if you have a watch and you want to know when something actually changed, you can have a lot of clients race in to kind of get that information. So we actually modified the code for our system to actually add jitter or splay on that so that not all of them kind of race back in at the exact same time to get the updated information about the services. And that really kind of helped because, for example, we had some issues with services that were monitored by a system like Supervisor or System D or Monitor or what have you. And usually in the application startup process, you only register yourself for availability to serve the service once you pass your local health checks and your availability is okay. We had one code that actually registered their availability first before they're actually ready to serve, and they crashed. So basically what ended up happening was that in production, you had a system that basically just kept getting restarted over and over again, creating all these notifications to the downstream services, and then all of the people race back in and get their information as fast as possible and kind of get into the same type of pattern where you get this thundering urgent going in. So even if you use another type of system, I would recommend we added hold down timers for our client code. So that means that if any change and the service happens, only let that happen every once in a while. So you can actually kind of do some load shedding on that, because not every service needs to know 10 times a second that its service registry changed. And then in general, I'm just going to go shout out to a GitHub project from the people at Twitter that we've been using in production and contributed to a little bit as well, called ZK Traffic. So if you're not familiar with this tool, it actually allows you to sit on an observer main quorum and look at the actual network packets themselves coming in to figure out what's going on. So you can see, do I have a flapping service that actually is going up and down all the time? How many things are entering the bypass? There's just a ton of rich metadata that we grab from that and we put inside our own monitoring systems. So if you're actually using Zookeeper at any scale, I highly recommend grabbing and using that code. And then finally, what I want to talk about is how the service discovery paradigms and the dynamic environment is kind of changing the way that we monitor systems at Pinterest. I'm actually kind of interested to actually hear from the rest of you with the new stuff that's coming out with containerization, how other people are choosing to kind of solve these challenges. But one thing that we've kind of done that was a good pattern that other people have done as well is we kind of standardize on a metrics interface. So what that means is that if you're providing an application, you're going to provide a unified place to actually grab metrics. So an example, HTTP example, you have stats.txt, which will return you plain text response new line delimited. You have something like stats.json, which will return you JSON-based stuff, or even stats.csv, which can work with some other type of tools. And the reason why that's a powerful concept is that when you marry that unified interface for getting all that information with service discovery, then service discovery kind of becomes the central port source of truth on actually what's running in your environment and then how to pull it. So for example, if you wanted to create some simple tool that kind of did some real-time ad hoc stuff for incident response, you can just query where are all the nodes servicing the service. And you get back a list of all IP addresses and ports, so they can go query the metrics interface and say, show me all gauges, all counters, all timers, or whatever have you for a metric for connections and timeless or errors. And then basically you got some ad hoc real-time reporting. And then in general, this pattern works well when you have multiple apps on a host because you don't have necessarily one single place to query for that information. And then the other one we've seen is that some other types of systems use configuration management to push that metrics collection data down to the host. And one thing that actually we had a question about is that if you're going towards a full container model or vice versa, and this environment is changing all the time, then how do you actually get the collector code down to the machine to know how to collect those? So with this kind of pattern, we actually can pull it out, so no matter where that is scheduled in our environment, multiple apps or whatnot, we can discover it, we can pull it, and grab the metrics from it, and we don't necessarily need to know anything else about it, which has actually been really, really helpful. And then also like pull-based systems in general for us are easier to kind of troubleshoot when we have metrics delivery issues. So a push-based system for us is kind of harder to realize why it's not. There's not a lot of load shedding, so maybe the thing that's actually collecting those metrics from you is down or overloaded. But with a pull-based system, we can say, yep, that system is unavailable. This is the last time I pulled it. So you can get a little bit more service level objective around your pull infrastructure, which we kind of found successful. And then in general, to kind of echo some of the other statements made by the other presenters, is the way that we kind of approach monitoring of Pinterest is actually more than just a time series database. And we've actually seen that we want to get in the mind of the person using the system to determine what is the best system for them to use. Examples when we're creating these type of metrics and telemetry systems, how does it work for first responders? How does it work for investigators or analysts? How does it work for service owners? Because all of those are different types of tools. So out there, I mean, I'm definitely a fan of pretty graphs and a lot of time series stuff, but there's a lot of other problems that also need solving as well. So for example, first responders actually need really high quality signal information. So when the site's down and somebody's saying, what's going on, need something that actually has really, really good rolled up, not raw data, but really good rolled up insights to figure out what's going on. Also, the timeliness of that system is really critical, and it does not necessarily have to be the most correct. One of the most painful things I think in my role as a site reliability engineer that I can experience is that something's wrong, and I do something to actually change to see if it had an effect, and then I realize that my polling infrastructure is 1 minute, and I need at least 3 data points, so now I got to wait 3 minutes to see if something actually made an effect. Whereas more real-time systems actually kind of give you a little bit more insight into that in real time. In addition to that, investors and analysts do capacity planning and whatnot. They need real high confident data. They can't actually have metric systems drop stuff, because if you're doing capacity planning or you're figuring out what happened as a post-mortem after the incident, you basically don't want to have something like a UDP-based system that drops your metrics that you have no reliability into. And then in general, if you're going to alert off of your time series database, it has to be really high quality. It can't lose data, it can't lose metrics. And of course, echoing some other people, it has to be more reliable in the systems it's monitoring. In addition, service owners need a lot of other things. So for example, how to deploy software to their services, how to do canary analysis, how to actually determine the overall state and health of their system. So those are different types of tools, not necessarily just one graph dashboard that rolls all. So I kind of got a little bit of some stuff, some of the things that we learned internally. So a lot of the things that we use for analytics actually has a lot of corollaries to the big data processing systems. So we have a data team at Pinterest, which is responsible for a lot of our business dashboards and business metrics and growth reports and whatnot. And we've leveraged a lot of their infrastructure to actually do a lot of our operational data. So for example, there's data cubes, there's drill downs. You can see, for example, what's the critical success point by a service. So like what's the feed service, what's that week over week, month over month. So this is information service owners need to see if they're improving the quality of their service. And then when they actually need to drill down into, like, show me what's the success rate on Android phones in Europe, they actually have the ability to do that, which is actually, sometimes they need things like that for analysts. And then a lot of it's refined and really rolled up data. An example, our logs have IP addresses and other information, which is not very helpful. But a lot of our processing systems will transform that to geo, or look up autonomous systems information for traffic engineers. So they do a lot more data, stuff with that raw log data, so they can actually provide those insights. In addition, service owners actually need some tools to actually help them operate their system on the fly. An example I gave before is how do you actually look up what the service map is. So when you register yourself for service discovery, how do you know that you're actually converge. So for example, you have a lot of hosts in your fleet. How do they get the memo? Do they get the update that everything changed? And like, you have tools to actually see that, so if there's any problems with your routing, you can actually introspect it. So we created one kind of tool to actually go out there and figure out what the convergence time is across the fleet for the service map, and basically what does everyone believe it is, and if anybody's stuck. So those are some kind of tools that we actually use that service owners can debug the connectivity issues with their servers or whatnot. Also, for example, classic time series, UIs, dashboards, deployment visibility, and also other types of tools that doesn't get a lot of shout out in the open source realm, like exception tracking and distributed tracing. So they're trying to figure out what's wrong with maybe a downstream dependent service that they're relying on. They have the information to actually exonerate themselves. They can say, yep, it's not my service, it's somebody else. And then some of the first, the real-time systems. So this dashboard is one that we kind of have at Pinterest when the site really goes south, that people kind of just go into and take a look at. This is fudge numbers. I would love to have that availability. But basically, what is that we have a kind of a general, really highly distilled, really focused site about all the general health of all of our services. It got cut off. This is a lot bigger than this. But basically, all the different services, core services that comprise the internet experience, the ones that require not optional services, and information about what is the total request per second on handsets and what area. In addition, on the right-hand side, you can't see on this one, but we do kind of analysis on worst performing hosts in the fleet, so you can actually kind of determine noisy neighbors. But basically, this is rendered by stream processing. So all of our log data that comes off of hosts will go directly to a Kafka topic, and then be streamed into the system, and then be distilled down to the cyclic sites. But I kind of just want to give a flavor of those things. And then before closing, I just have some final thoughts, and thanks for listening. But basically, what I want to say is that we're Monitorama with a lot of really intelligent people in this room. I'd love to actually see what everyone's thoughts are, and just kind of focusing not necessarily on the time series databases, which everyone likes the pretty grasp, but other types of the scalability system. Also, how the scalable backends really come into play. An example, one issue and challenge that we actually have is that with all this dynamic data that is around, we have to do effective roll-ups and summary data, because these hosts might only be alive for 4 hours to serve your service. And they collect an amazing ocean amount of metrics. It's almost like big data. One host can actually just put an amazing amount of stuff out there. So then how do we make sure that we roll that up into more intelligent stuff and remove that? Because it's not really helpful to actually have these host metrics around in a really dynamic ephemeral environment like that in perpetuity. So for example, RRD-based systems, which they create one data point per host or per metric, then they actually may run out of disk space in their system just because of the amount of just temporary stuff that's actually being developed. And then in general, I kind of said a little bit before about reliable data delivery. It's a kind of a hard lesson that we learned early on, is that when people lose confidence in your availability system, your observability system, it really kind of hurts your image. An example is, I would love to alert off this stuff off your telemetry data inside of your time series database. Well, they're like, well, is this an incident, or is this the metrics that dropped? You know, and if you're in that type of mode where nobody actually has confidence that you actually saw that, then you really can't alert off that data because it's not actionable. So I think there's a lot of things that we actually need to do to make sure the reliability of the system is key. And in general, also containerization. So it's something new that everyone's kind of taking a look at. But how will it change the scope of how to actually collect this metrics data and actually visualize it? And then in general, there's just a lot of stuff out there, and I'm kind of excited to hear what you guys are all thinking about. And then final pitch, we're hiring, like everyone else in this room that we're hiring. I work for cloud engineering, but if you're looking at solving some of the visibility challenges, dev tools, pretty much all these visibility and observability tools, we have more than enough work. So with that, I'd just like to say thank you for your time, and I'll just take a couple questions.
Can you talk a little bit about TCP
Sure. So the question was TCP tuning on the observers themselves. So we don't really do anything. We just kind of do the standard run-of-the-mill tuning. If you want some load chain stuff, the TCP board on overflow can help, but ultimately that should save you from a bad situation. A lot of it is the Zookeeper stuff is keeping the connections alive, so that timeouts and the keep alive and whatnot. So we make those a little bit more elevated, a little bit more relaxed, but ultimately it's a live, active connection. So that means that they're actually pinging and heartbeating themselves. So there's not too much required to actually keep them up and stable, because depending on your configuration, every couple of seconds, they're notifying the threshold sample. Cool. Question?
So this is always a fun challenge when it comes to service discovery, is what metadata is actually interesting for you, what metadata you store as far as, when you're storing service discovery. So you have, of course, the IP, obviously the service name, the owner, What else?
Okay, the question is there any additional metadata you put in your service discovery system just besides the information to connect to a service? So basically the way we kind of tackled it is that we could put the health check information inside of the service discovery system, but ultimately we employ a lot of techniques in the client, and the client's a pretty intelligent load balancer. Okay, we'll do stuff like circuit breakers or load shedding techniques or fail fast, and also knowing if exceptions are non-retriable or retriable exceptions. So ultimately we try not to put as much health logic in the service discovery system because the view of the health of that service really relies on the client. So the client may be in a different place where maybe it's firewalled off from this host. So if we put it's healthy, maybe that client says it's not. Maybe it's in a data center that can't connect with it or vice versa. So ultimately, in our opinion, the best source of truth at this time for a service discovery system is to have the clients actually know the health of the system and actually respond to that.
Well, when you're trying to get data from there.
Oh, actually, we're out of time, but if you want, we can check in the hallway. Cool. Thanks.